Hey guys, I would be giving a quick summary as to what Unit 2 actually means. Right now, from the classes, what we've observed, we've just seen people dealing with matrices, but we do not have a comprehensive understanding as to how and why the matrix actually came up. So, I would be giving a quick summary as to how the derivations actually have taken place and how do we solve problems from them. So in Unit 2, the heading starts with a macromechanical analysis of lamina. So when I talk about macromechanical analysis, see, it's a form of study. When I say macromechanical analysis of lamina, I do not consider the entire laminate. I follow my study by just considering simple layers of laminas, and then I would elaborate my study by just integrating functions. Okay. Now, before we dwell into the topic, I would just like to start with a few terms which everyone might be aware of, but just as a small recap. The first term is stress. Stress is nothing but the ratio of the force upon the area. When I talk about strain, strain talks about the deformation per actual length, what the substance actually had it. When I talk about modulus of elasticity or Young's modulus, it's the ratio of normal stress to the longitudinal strain. And Hooke's law, we've already read. Hooke's law states that stress is directly proportional to strain. So I could write stress is directly proportional to strain. To remove the proportionality, I can plug in some constant. Okay, so that's what Hooke's law says. When I talk about isotropic material is like if I talk about any substance and I measure the properties of that substance with respect to any direction, the properties remain the same. For example, let's say this eraser is an isotropic material. Now, if let's say the eraser also has some Young's modulus or some shear modulus. If I measure the Young's modulus of this eraser in x direction, y direction, or z direction, the Young's modulus will always have the same value. Similarly, the shear modulus and the other engineering constants would say the same. So basically, isotropic materials states that the properties of the material would stay same irrespective of the direction what you're measuring. When I talk about anisotropic material, it's just the opposite. See, the properties change with respect to the directions. Now, uh, our main motto of this chapter, I mean, of this study, macromechanical analysis, is that we develop a good, a healthy relation between stress and strain through which we can compute uh, or we can analyze the laminate. Okay, so we do all this analysis based upon Hooke's law. Okay, so let's start. So let's take a particular section, let's say a cube, and we will find the relation between stress and strain and then integrate it so that we get the analysis of the entire laminate. So we would be taking a small element and then elaborating our study. So if this is a cube and let's say this is the direction x, this is direction y and direction z, I'm representing it with constants 1, 2 and 3. Okay, so anything in here, the first thing represents the plane, what the force is acting, and the second one represents the direction, right? So before I explain this, let me tell you two terms: shear stress and normal stress. So if you see this table in here, if any force acts on the surface of the table, it's called shear. And if there's any stress which is acting perpendicular to the direction of the table, it's called normal stress. Okay, so generally, if we just consider this cube and this particular box as the first plane, the plane is one. So there are basically three stress components. So stress in plane 1, stress in plane 2, and stress in plane 3. Why are there three components? Because each component acts along each direction. Let's say sigma 1 acts in the first plane and towards x-axis. Sigma 1 2 acts in the first plane and towards y-axis. Sigma 1 3 acts in the first plane and towards z-axis. Similarly, if I talk about plane 2, the first notation would be 2, and sigma 21 is acting in the second plane towards x-axis. Sigma 22 is acting in the second plane towards y-axis, and sigma 23 acting in the second plane towards z-axis. The same thing in plane 3, 3 1 third plane z-axis, third plane y-axis, third plane z-axis. Okay, so basically now we've seen that one cube, like one infinitesimal small particle, has got a total of 9 stress components, right? Out of which 3 are acting in the directions. See, 1 is acting in this direction, 1 2 is acting in this direction. I mean, they're aligning with the axis, right? 1 1 1 2 are aligning with the axis, 2 1 2 2 are aligning, 3 1 and 3 2 are also aligning with these axes 1 and 2. But 1 3 2 3 and 3 3 are protruding out of the surface in this way. So we can say that 1 3 2 3 and 3 3 are the normal stresses, and the rest all are the shear stresses. So we have a total of 3 normal stresses and 6 shear stresses, giving us total 9 stress components, right? So similarly, we would also be having 9 strain components. So this is a basic analysis of the cube what we consider. Now, we from Hooke's law, what I already told, we know that stress is directly proportional to strain, right? So I would write my stress function as a function of any amount of strain, right? I've actually I need to write sigma 1 2 sigma 2 1 sigma 2 3 so on, but I've just computed it with notations I and j, right? So I and j would be a function of any of these 9 stress components as well, right? So in order to remove, in order to describe a particular entity, instead of this function, instead of writing stress as a function of strain, I would be writing stress ij is a function. Instead of the function, I would be writing this constant, which is actually a matrix Cijkl times stress, strain kl. Okay, I hope it's clear till here. So we've seen Cijkl as a matrix. This acts as the stress and this acts as the strain. Now these two components K and L are repeating. So Einstein notations state that when any component, when any variable is repeating, we can condense it by writing the summation. Okay, so I would be writing stress as a summation of, because K and L are repeating, I would be taking the summation of K and L. So K from 1 to 3, L from 1 to 3, Cijkl times strain KL. Since we might be having a doubt, why are we only restricting it to 3? Since we've got only 3 planes of study with X, Y, and Z, we're just taking 3 planes, okay? For us to understand this relation better, let's take the stress component sigma 2 3, okay, wherein I is 2 and j is 3. Just plug in the values of 2 and 3 wherever you see I and j respectively. So I would write k from 1 to 3, L from 1 to 3, C23 KL times strain KL. Now if I have to elaborate my study here and remove the summation, and I would go on placing k as 1, k as 1, k as 1 2 3, L as 1 2 3, and this would be my summation. Alright, so sigma 2 3 can be represented in this manner. You can see C23 stays constants. In the first place, in the first 3 readings, K took 1, 2, K took 1, and L moved on from 1 2 3. In the next 3 readings, K took 2, and L moved on from again 1 2 3. And the third reading also went the same way. So in summation, what I can say is that one stress component can be written as a sum of 9 strain components. If you see here, we've got 1 2 3 4 5 6 7 8 9 strain components. So here what I can write as my 9 stress components, what we've seen in here, can be written as the Cijkl matrix times the 9 strain components. The Cijkl represents this function, right? So we've got 9 different constants, and we've got 9 different for each of the 9 stress components. So we've got a 9 by 9 matrix, which is a total of 81 elements, right? 81 constants. So my stress and strain can be related through a matrix which has got 81 constants, and that is what is your Hooke's law states, okay, in composite materials. Okay, so basically what Hooke's law states in here is, to relate the stress and strain, we need 81 independent constants. But I and you, everyone know that computing 81 components is practically impossible for just one layer. So we need to simplify our study further to the maximum extent possible, right? So what I would be doing is that I would be considering an equilibrium such that Ij and Ji would be the same. That is, if I write 2 3, it would be the same as 3 2. 1 3 would be the same as 3 1, and 1 2 would be the same as 2 1, right? So there is some equilibrium what we are assuming. Okay, so instead of writing 1 1 1, I mean, instead of writing 3 1 and 1 3, I would be just taking it as one element. I wouldn't be writing it twice. Instead of writing 1 2 and 2 1, I would just be considering one element instead of taking two different elements like 1 2 and 2 1. So these 9 elements can be reduced to 6 elements, because ultimately 3 1 and 1 3 is the same. So instead of writing 2, I'll just write 1. Okay, 1 2 and 2 1 is same. Instead of writing these two, I'll just take 1. And 3 2 and 2 3 are same. Instead of writing these two, I'd be just taking 1. So these 3 elements plus 1 1 2 2 and 3 3, I would be having a total of 6 elements, right? So I only have restricted my study from 9 stress components to only 6 stress components. Okay, so I've got my 6 stress components, I've got my matrix, and I've got my 9 strain components. Now, since I'm neglecting the last 3 stress components, that was 3 2 3 1 and 1 2, I would also be neglecting the last 3 rows in here for the matrix. Therefore, what I would be having is I would be having a 6 row but 9 column matrix, and I would be having a 9 column and 9 row and 1 column matrix here. Okay, so if you see, we had 81 elements. 9 by 9 results in 81. Here I'm just taking a 6 by 9 which has 54 elements. Now we've significantly reduced the number of elements from 81 to 54. Now, since I am considering this equilibrium for stress, I would also be considering the same equilibrium for strain. So instead of taking 9 elements here, I would be only taking 6 elements here. I would be eliminating, the terms like 2 3 and 3 2, I would just take it as one term. So since I am eliminating the last 3 columns in here, I would also eliminate the last 3 columns in here, because they're redundant again. So I would be having a 6 by 6 matrix. So I would be having a 36 element matrix now. Now see how fast we are actually reducing. From 81 elements, we've come to 54 elements. And significantly, we've dropped to 36 elements. Now, the rate of dropping of elements from here would be a little slow. For our further convenience, we would be analyzing a study like taking 1 1 2 2 3 3. All this is a little tricky, so we use a contracted notation. Contracted notation means nothing but, instead of writing 1 1, I just write as 1. Sigma 1 is nothing but sigma 1 1. 2 is nothing but 2 2, and these are the contracted notation terms. So instead of representing it with these terms, I use a single number to notate these terms. The same applies for strain. Okay, now in order for me to summarize, I can write my 6 elements of stress as a 6 by 6 element matrix times my 6 elements of strain. When I'm relating stress with respect of strain, I call my C matrix as a stiffness matrix. And if I'm relating the reverse, that is, if I relate my strain with respect to some matrix times the stress, I would call it as my compliance matrix. The relation between this stiffness matrix and compliance matrix is that both of them are inversely proportional to each other. But see, again, who would want to actually compute 36 elements? I would try to reduce it further, right? So we use a function which is the strain energy density function. Now, what does this postulate say? The postulate says that when I derivate my strain energy with respect to any strain component, I should get my stress. So this is a postulate which is already given by people. It's not something we are assuming. So let me get it to you once again. When I differentiate my strain energy with respect to a strain component, I should get my stress. Okay, but also we can write our stress component as any element, let's say Cij times my strain. So I can write my stress as this. So basically I can equate both of them. So I can write dou W by dou Ei, Cij times Ej. Now we take two cases. The first case is where I differentiate it with respect to strain component Ej, and the second case wherein I differentiate with respect to strain component EI. So when I differentiate with respect to EJ, I get CIJ because dou EJ by dou EJ is 1. And when I differentiate with respect to EI, I would be getting CJI as my component. Since the derivative should be equal, because practically I'm derivating the same function in two different manners, the answer should be same. I would be getting Cij and Cji as equal, because that's the final relation what I can reduce. So which means, like, if I can say C1 2, let's say I is 1 and j is 2, C1 2 would be same as C2 1, right? So that is the reason why I'm eliminating the lower triangle matrix here, because 1 2 is same as 2 1, 3 1 is same as 1 3. So I can just neglect these terms because they're just mirror images of these terms. So if I have to see, we had 36 elements in here, we reduced it to 36 elements. But now if you see, I've got 6 elements, 5 4 3 2 1. If I add all these up, I just have 21 elements now here. Okay. So the same for the strain matrix as well. I would be just having the upper triangular matrix, which is 21 elements. So in summary, I've got my generalized Hooke's law, which stated that we need 81 constants. My stress symmetry matrix, we got 54. Then when we consider stress and strain symmetry, we got 36. And finally, we got 21. Now in the next video, I'll be telling you how you can actually reduce these elements to the most possible extent.